as an application example how you can use Gauss law to find an electric field due to an infinite line charge. This is infinite in length, and it has a certain charge density rho L, which is Coulomb per meter. It's uniformly distributed along that line. That means if I take any point, it's uniform charges that are distributed along that line. And I want to find what is the electric field around that. Clearly, you guys know that if I have a charge distribution like this, and if I find the electric field at this point, any point, since this charge is, since this line is infinitely long, I can always choose for any point that I choose above this point here. There is always another point that is at a lower distance here, which is like a mirror to it, isn't it? So the electric field due to this guy is going to be along this direction. The electric field due to this guy is going to be along this direction. This vector and this vector and I will end up getting one vector in the direction of, in this particular direction, isn't it? So now you're going to look at thin line along the z-axis. You want to find the electric flux at any location. You want to find an electric flux at any location, for example, electric flux density D at any location. So you can go ahead and naturally think about a Gaussian surface, which is a cylinder. And you kind of know already that for every point here, this vector and this vector cancel each other, and you will get only one vector that is pointing outward anyway. What will be the direction of this vector in cylindrical coordinates? If you were to take a look at this with the eyes from here, right? If you were to take a look at this, what you see is a dot of current plus rho L. All the flux are going to be pointing in this direction, isn't it? What this direction is in cylindrical coordinates, it's rho hat, isn't it? The direction in which rho changes is rho hat, yeah? So it's going to be in the rho hat direction. So in a way, you kind of know what is the D vector is going to be. It's in the direction of rho hat. But how do we do this now? Due to symmetry of line charges, consider a cylindrical Gaussian surface of height h. The charge enclosed by this Gaussian surface is going to be, since this is going to have rho L Coulomb per meter, but this is having h meters. If I want to find the total charge enclosed from this point to this point, if I want to find what is the total charge enclosed, that is going to be rho L times h mark, this many coulombs. So due to symmetry, we see that the phi is going to have only a rho hat direction, D is going to have only a rho hat direction. And do you think that it will depend on phi and z? Certainly not, right? Because this is an infinitely long wire. Whether you're measuring here or here or here or here does not matter. It's infinitely long. So z dependence is not there. It is independent. Does not depend on z. And this guy is a symmetric structure, whether you are at this point in space or this point in space or this point in space that is equally far from this wire, the phi angle does not matter. That means this phi angle does not matter. Whether it's this point or this point or this point or this point, you are independent of phi. And it only has the rho hat direction. It only has the rho hat direction. So I call it as d rho hat. Then you apply the Gauss law saying that, hey, this is my d dot ds. You guys know that for this surface, the ds is, this ds is going to be, rho is fixed. Rho is fixed because, you know, for a cylinder at the edge, surface of the cylinder, the rho is fixed. So rho is fixed. That means the two others are changing, which is d phi and dz. So you make it rho d phi and dz, and this is in the rho hat direction. So when you go ahead and do that, your z is changing from 0 to h, 0 to h, phi changing from 0 to 2 pi, 0 to 2 pi. This is your d from here, and this guy is your ds from here. You notice that rho hat dot rho hat is equal to 1, so this whole term goes off, and you simply have d rho d phi dz, and you notice that this is equal to the total charge enclosed, which is this guy. The total charge enclosed is going to be rho L h. So you can go ahead and play around and find your d rho to be rho L over 2 pi rho. So then you find your electric field to be d over epsilon naught, because you know that d is epsilon naught E, because in this case it's free space or vacuum. Epsilon is epsilon naught. Then you can go ahead and find the electric field expression. So this expression that you get will be exactly the same if you were to work out the q over 4 pi epsilon naught r minus rq, the line charge law. If you were to do the line charge integration, yeah, that is what you would get. If you were to do the electric field by that kind of integration, this is exactly what you will get. This result and this result will be the same.